In this video, we will do an example involving a car that has triangular tires that start to rotate. So the question says that an inventor builds a model car with tires in the shape of equilateral triangles of side length 2 inches. She sets up a laser 1 inch behind the back of the rear tire. I'm going to call that vertex B, where the back of the rear tire is, which is flat on the ground. So that the rear tire is flat on the ground because, you know, it's a triangle shape, so it's going to be this orientation where this is flat on the ground. All right, and after 3 seconds now of turning at a constant rate, the back of the tire has lifted square root of 3 inches off the ground. At what rate is the distance between the laser and vertex B changing at that instant? So definitely give yourself like a minute or so to copy this problem down, because I'm going to move to the top of the page so we can start drawing a picture. All right, so there are 2 situations being described here. There's kind of what's happening initially, the initial orientation, and then there's what's happening after some amount of time, after 3 seconds, because the tires start to rotate. All right, so I'm going to draw an initial picture. So I'm going to draw the ground. So I have the ground. And then somewhere on the ground we have this laser. So let's say here's where the laser is. And the laser is 1 inch from the back of the triangular tire. So I'm just going to draw one of these triangular tires in the car. So the laser is 1 inch away from the back of the triangular tire. And the problem told me that the triangular tire lies flat on the ground initially. So it's not going to be something like that, because then it's not lying flat on the ground. It's got to be in this type of orientation. Okay, where one of the sides is lying on the ground. Alrighty, and the problem told me to call the back of the tire, which is here, vertex B. Okay, and we were given that the sides of the tire, these lengths of the triangle, were all 2. And initially, the distance from the laser to that vertex at B was 1. Okay, so initially, we had a picture like this. So at this point, I want to have you pause the video. Quick pause for 3 minutes to see if you can draw this next picture, what it looks like after 3 seconds, and then if you can write down the rates that we know and the rate that we want to find. Just up to there. 4, 3, 2, 1, pause it. Try to draw the picture after 3 seconds, and then write down the rates that we know and want to find. All right, so after 3 seconds, I will draw the ground. And then we have the laser on the ground. So let's label that as where the laser is. And then the tire will start to rotate. So when it rotates, the problem told me that the back of the tire is going to start to lift up. So this is going to start to lift up this way. And that means the tire is rotating or pivoting about this point. Okay, so after a little amount of time, you know, it'll move to an orientation like something like this. The back will have lifted up a little bit. Okay, so I'm going to start to draw a picture of that. So it'll be some, you know, it'll have lifted some amount like this. Okay, so my triangle will be this orientation. So this is 2, this is 2, this is 2. And this is vertex B. And now I want to assign variables and label any other quantities that I know. Okay, so I'm going to label this point. I'm just going to call this point P. And point P hasn't changed. And one thing I know is the distance from the laser to point P. Because looking at my initial picture, the distance from the laser to B was 1. And from B to P was 2. So if I add those together, we get that this distance from the laser to P is 3. All right, so we know that. Okay, so one thing that's going to be changing is this angle. I'm going to call that theta. As the tire rotates, that angle definitely changes. The question is asking at what rate is the distance from the laser to that back point of the tire, which is B. At what rate is that changing? So I'll draw a straight line connecting them. And I'm going to assign a variable to that because that length is changing and I care about it. Okay, and then after 3 seconds, it tells me that this point at B, the back of this tire, this is root 3 inches off the ground. So that quantity, that height is changing, but at that instant, I just want to keep in mind, that height is going to be root 3. So if I do need to plug something in or later, I'm going to use this root 3. Okay, so we are ready to write down rates that we know and the rate that we want to find. Okay, so the rate that we know actually has to do with the angle. Because the problem tells me that the tire is turning, it's turning at a constant rate. And it tells me that after 3 seconds of turning, so some amount of time elapses, it tells me, how much is it lifted? So maybe I can use that to figure out what d theta dt is. All right, so we know d theta dt, at least we can figure it out. We'll be able to figure it out. And because the tire is turning at a constant rate, I can figure out d theta dt by just doing the change in theta, how much the angle changes, over the change in time. So this is an average rate of change, and the average rate of change just so happens to be the instantaneous rate of change. That's the derivative. That's only true when that instantaneous, that's only true because this rate is a constant. So this is true since the rate is constant. All right, so I know the change in time to get to that new orientation is 3 seconds. So how much does the angle change? Well, I need to know how big this angle is after 3 seconds, when b is root 3 inches off the ground. So to answer that, I'm going to draw a vertical line like this, and that makes a right triangle, which I'll draw up here. And this right triangle, this is point P, this is point B, and I know that this length is root 3, and I know that from B to P, that's just the length of my triangle, side length, which is 2. And at this point, we might recognize what type of triangle this is. This is a special triangle from geometry. It is a 30, 60, 90 triangle, where this is the 30, and this is the 60. So I have to remember some geometry for this question. The missing side of this triangle, I could either remember from 30, 60, 90, or I could do Pythagorean theorem. The missing side is 1. So that tells me that after 3 seconds, this angle theta has become 60 degrees. So that's how much theta changed. Let me write that in radians. So this is going to be pi over 3 radians. And it's actually very important that we use radians here, not degrees. And it has to do with the fact that the derivatives of trig functions, back when we first derived those formulas, we need to be working in radians for those formulas to be what they are. It's actually one of our optional homework problems to investigate why. Why do we need radians and not degrees? All right, but nonetheless, let's simplify. So pi over 3 divided by 3, that's going to be pi over 9. And this is in radians per second. All right, and this should be positive because that angle theta is getting bigger. Positive since theta is increasing. And what I want to find is dc dt, the rate at which that length c is changing. And I want to find it at the instant when b is root 3 inches off the ground. So we're at the point where we need to now set up an equation. And we want the equation to involve c and to involve theta. So it's probably going to involve this, triangle. So this triangle here is probably going to involve that triangle. But that triangle is not necessarily a right triangle. Okay, so we need some equation there. And I want to give you a chance, quick pause, 1 minute, to think about, what equation can I set up that involves an angle when my triangle is not necessarily a right triangle that also involves this opposite side? We're really going to have to dig into our pre-calc knowledge for this. 4, 3, 2, 1. Quick pause, just a minute to think about that. All right, let's talk about it. Okay, so this is I'm going to give a general kind of recommendation or hint about this. And that is to note that when theta and our side of the triangle are not, when they are not in a right triangle, we will try either the law of cosines, this is something from pre-calc or trigonometry, or what's called the law of sines. Both of those set up relationships between sides and angles in a triangle, even when it's not necessarily a right triangle. Okay, so for this problem, I'm going to do law of cosines. Law of cosines. So let's review what it says. All right, so I'm going to draw a triangle. Draw a triangle. I'm going to make it hard to, I'm going to do my best to make it look like not a right triangle. And I'm going to call this angle theta. And I'll call this B, this A, and this C. The law of cosine says that C squared equals A squared plus B squared minus 2AB cosine of theta. All right, so that is the law of cosines, and we're going to use this as our equation here. All right, so we are ready for the equation. So in our picture, we're going to do that on this triangle. In this triangle, this side length is C, and then the other two sides, we know, they're constant. This is a 2 and this is a 3. All right, so if we do law of cosines there, we will get C squared equals A squared is 2 squared, and B squared is 3 squared. If I switch the order of the 2 and the 3, that's fine. And then minus 2 times A times B, so 2 times 3, those are those other lengths, times cosine of theta. All right, and now let's simplify. We get C squared equals 4 plus 9 is 13, and then minus 2 times 3, that'll give me minus 12, and then cosine theta. Okay, so we got an equation. Now we're ready to differentiate. So d dt of the left is going to be d dt of the right. All right, so d dt of c squared equals d dt of 13 minus 12 cosine theta. And we're ready to differentiate implicitly. Derivative of c squared is going to be 2c times dc dt. On the other side, derivative of 13 is 0, because that's a constant. And then the derivative of cosine theta is going to be minus sine. So the minus is going to cancel this minus. So I'll get positive 12 sine theta. But then I have to do chain rule and multiply by the derivative of the inside thing, the theta, and that is d theta dt. Let's rearrange this a little bit and simplify. Okay, so I can divide both sides by 2. That'll cancel this 2 and make that 12 become a 6. And now let me divide the c over, because I want to know dc dt. So dc dt is going to be equal to 6 sine. And now that I've taken the derivative, now I can plug in specific values. Remember, my theta at this instant was pi over 3. d theta dt, we had figured this out earlier. This was pi over 9. That was in radians per second. And then we've divided the c over. Okay, so we know everything except for the c. We need to be able to figure out what c is. So what this length c is at this instant. And the way we're going to do that is we're just going to use our equation, this law of cosines equation, but with everything plugged in, and then figure out what c is. All right. So we use law of cosines to solve for c. And that general technique, we've seen it before, just in terms of using whatever equation we had to figure out some missing unknown value. All right, so we'll get c squared equals 2 squared plus 3 squared minus 2 times ab, 2 times 3, times cosine of the angle, which was pi over 3. All right, so we get c squared equals 13 minus 12 times cosine of pi over 3, and that's 1/2. All right, so we get c squared equals 13 minus 6, which is 7. And if I square root this, we get c equals root 7. I don't need a plus or minus because c is a length. So no plus or minus since c is a length. All right, so dc dt is going to be equal to 6. And then sine of pi over 3 is root 3 over 2. And then times pi over 9. And then we get this divided by c, which is root 7. So if we simplify this a little bit, with the 6 and the 2, I could cancel. I'll be left with a 1 down here and a 3 here. And then with the 3 and the 9, I can cancel and have a 1 here and a 3 here. So what this gives me is I'm left with a root 3 and a pi on the top. And on the bottom, I'll be left with 3 root 7. And the units so I have the units of c on top, the units of length, which were inches in the problem. And the units of time in the question were seconds. And that is my answer. So as far as related rates problems go, this is definitely on the more challenging end. So if you couldn't quite follow everything on this first go around, that's totally okay. Definitely rewatch this, pause the video, go through it at your own pace. When you have questions, definitely use our resources like office hours and SLC tutoring to come ask about it.